Alright guys, balancing chemical reactions. We're almost done chemistry. Having just done reaction types, now we have to figure out how we can put these things together.
Alright, so balancing chemical reactions is all based on the law of conservation of mass. For study purposes, it's like the law of conservation of energy that we talked about. Okay, mass always has to stay constant in a chemical reaction.
Kind of like energy had to stay constant in a system back in physics. Now, what does that actually mean? Well, as you can probably read, all of the mass in a chemical reaction has to be preserved. No little atoms are allowed to go missing. Matter cannot be created, it cannot be destroyed. As Jackie Chan is having trouble understanding. Now, essentially what this means is there's no chemical fairy. If we look at your balanced equation, everything has to balance. This chemical fairy can't show up to take things away. The chemical fairy also does not show up to magically make things appear just because you need them.
So if you have a certain number of atoms of an element in the reactant side of a chemical reaction, the same number of atoms must be present on the product side as well. Okay, this applies for all types of atoms, elements, compounds, anything like that.
So, to just quickly jump to some examples. Guys, this is mostly a skill. This isn't a theory. So we're going to go through this pretty quick and try to hit some examples because this is where we can actually help you. One method for trying to balance equations. Here we have carbon and oxygen as a word equation. We've already written it out as a chemical equation with our symbols to show that carbon and oxygen can form CO2. So if we were to just look at this, we can create a table. Now the way we normally create the table, emphasis right here, separation from reactants and products. If something exists as a reactant, it also must exist as a product. So now I can list all the species that are present. Here I have carbon. On this side I have carbon. Here I have oxygen. On this side I have oxygen. Now if I'm looking just at the carbon, on this side we have one carbon. On the right side we have one carbon. So at the moment carbon is balanced. If we look at the left side for oxygen, O with this little 2 here means we have 2 oxygens. When I look on the right side, my oxygen still has a 2. So at the moment, because the carbons are the same and because the oxygens are the same, this is already balanced. These ones are nice. Not every balanced equation requires you to put numbers in. You have to be able to look at them and realize that, oh, geez, that might already be balanced.
Okay, one thing you want to make sure, Mr. McLeod did a pretty good job there. Okay, when they are already balanced like that, you do not need to put a 1 as the coefficient leading into the question. It's already implied if you leave it blank. Okay, so that's just one thing to remember for an exam. Now we're going to take a look at a decomposition example. Water broken down into its elements of hydrogen and oxygen. Okay, as I can see, I've already got a kind of a weird looking H there. Okay, but we have our overall equation written right here. Okay, we're going to break it up just like we saw Mr. McLeod do. Okay, we have our reactants and our products. Okay, we're going to draw our table and get ready to go. Okay, we have to identify on both sides. We have hydrogen and we have oxygen on the reactant side. We have hydrogen and oxygen on the product side. Now we have to count. Okay, on the product side we see 2 hydrogen. Okay, and then we see 1 oxygen.
How do you know there's only 1 oxygen, Mr. Ray?
Well, if you take a look here, there's no subscript right beside the oxygen. However, just like the coefficients we just talked about, if there's nothing there, it's implied that there is 1.
Remember your naming.
Remember naming. Big, important part. Okay, on the other side, we take a look. We have 2 hydrogens and 2 oxygens. So obviously, we have the proper number of hydrogens that we need, but oxygens are going to be tricky on us now. So, in order to properly balance this out, we are going to have to change the number of oxygens on this side. So, we're going to start by throwing a 2 up front. Okay, now what the 2 does is it distributes into both of these guys. Okay, so now we have 2 times 2 gives us 4 hydrogens. Okay, and now we have 2 oxygens.
Good,
okay.
You finally balanced the oxygen. We're done now, right?
Funny one, Mr. McLeod. That's good. We're balanced here, but now we have a problem right here because we have 4 on the reactant side and 2 on the product. So, easy to fix. We need to fix this guy over here, and we know that 4 is divided by 2. Okay, nice and easy. We throw a 2 in front of here, and we end up changing this to 4, and we are off to the races. Okay, everything balances out. We end up seeing 4 hydrogens on both sides, 4 oxygens. The law of conservation of mass is good to go, and we're ready to move on.
So, as a quick note, guys, and this is color-coded to help you out, we have subscripts that come after the element, like that Cl2, and we have coefficients that come before a molecule. So you have to be able to distinguish what these numbers are. And we also need to know that when we see a subscript, that implies how many atoms we have. For example, in the red, 2 chlorines. Once we put a coefficient out in front, we actually need to, as it says right here, we need to multiply the subscript by the coefficient. In this example, on black, we actually have 4 chlorines. 2 times 2, not 2 plus 2.
And a special thing to remember, guys, that if no coefficient is present, okay, we treat it as a 1. Okay,
Same
so all the
with the
rules still apply.
subscripts.
Yeah, same with the subscripts.
How do you know when a 0 would be present, guys? Well, if there was a 0 as a subscript or a coefficient, that would mean that you just don't write it because there aren't any. The reason we have written it is there is at least 1. All right, another example. Magnesium is placed in hydrochloric acid. Now, this one is something that we often do as a nice single replacement reaction. When we go to do these, guys, if you were writing this out, we could start looking at this and saying, yes, we have magnesium, yes, we have hydrochloric acid. We still have to be careful. If we were to look at this one, this is not magnesium chloride. We have to follow our naming rules. If we look at this, magnesium actually has a charge from your table of +2. Chlorine has a charge of -1. So in order to actually make magnesium chloride work here, there needs to be a 2. Is this a common mistake that you're likely to make? Absolutely, it is. But that being said, naming rules still apply. Just be careful when you have to predict or write any equations. So we're going to separate. We know reactants are on the left, products are on the right. You don't have to write that. That was just the first couple to help you out. We have magnesium because there's a capital M. Capital H means I have hydrogen. Capital C means then I also have my chlorines. And I hopefully, if there is no chemistry fairy, will actually have the exact same things on this side. So first run, I'll just fill in how many I have. I have 1 magnesium, 1 hydrogen when the pen works, and 1 chlorine. On the right side, we have 1 magnesium, 2 chlorines, and 2 hydrogens. To balance any of these, guys, start looking at the things that look the biggest and most complex first. If I was to look at this, I've got magnesium looking okay, but my hydrogens and my chlorines are in trouble. So I got to fix them. I'm going to look at this guy first because he has this little 2 on his chlorine. So if he's got 2 chlorines there, I'm going to need to have 2 chlorines over here. To make 2 chlorines, I'll put a coefficient of 2. Now that works out great, except just like the water problem, that 2 is also applied to this hydrogen, so now I have to change the hydrogen to 2. In this case, that's actually a good thing. I don't have to go and do any more work. I am balanced. Everything looks great.
Woo! All right, so let's take a look at a double replacement reaction. Nice quick little example here. Okay, we have sodium hydroxide and phosphoric acid mixed to form sodium phosphate and water. We've already pre-written the formula for you. Again, this looks a little more complicated, but it brings up some important points that we have. We always start with the compound that has the most pieces involved. Okay, start complex, and hopefully it ends up working out for you. Okay, when we start taking a look at this, we separate just like before. Okay, we draw our line.
Sorry, I extended the page on Mr. Regnier there while he was writing.
So we have sodium on one side, OH, hydrogen, and PO4. Okay, now here's a good rule of thumb, guys, with these double replacement reactions. Okay, here's a good rule of thumb with the double replacement reactions. Now, if a polyatomic exists both on the reactant side, okay, and the product side, we can treat it as one. Okay, so if we take a look at PO4, we see PO4 on both sides. We can treat it as one instead of splitting it up into phosphorus and oxygen.
But Mr. Regnier, I don't see where that hydroxide shows up on the other side.
Well, Mr. McLeod, hydroxide would be in H2O, just like we talked about before. Okay, it's hydrogen and OH minus. Okay, so again, it does show up on the other side, so we can treat it the exact same way. Okay, so a nice little important point to remember. So now again, we see sodium, we see the OH, okay, H, and PO4. Okay, again, I just write them in order so that we can easily compare them as on the table. Now we count them up. 1, 1, 3, okay, and then we have 1 PO4. Okay, again, on this side, we see 3 sodiums, 1 OH, and 1 hydrogen, and 1 phosphate. And now we're off to the races. Okay, we obviously see OH is fine, PO4 is okay for right now, but we got to focus on these guys. Okay, big problem. Okay, so what we're going to look at is we're going to look at the most complex part first. So we're going to start with this guy. Okay, so let's start there. Okay, so we know that there's 3 sodiums on this side, there's 1 phosphate, so let's take a look and move over here, and we are going to look and compare this guy. Okay, so let's throw a 3 in front of there, like so. We'll do a different color, make life a little bit easier. Okay, so now we have 3 sodiums, but remember it goes into both of these guys, so we see 3 here as well, and we just made ourselves a little more complicated.
Well, that's good, because now we'll be able to take away this guy. We're okay on sodium. Instead, we have our problem with our hydroxide.
What next, Mr. McLeod?
Well, you know what? We've kind of looked at sodium, so I guess now we might as well go fix that little hydroxide problem. It's the next one down on the list.
Sure.
So 3, 2, well, let's make him a 3. How do we make this a 3? Now, guys, this is really important. When you're balancing double replacements, or even single replacements, and you see water, think about it as HOH, because I need to put a 3 in front of the water. That means that there are 3 of this hydroxide. What that creates is 3 hydrogens now as well.
Oh, Mr. McLeod, we just took care of both our problems at once.
Perfect. Now, guys, what you should find with most of your balancing is as you get near the end, as things start falling into place, that should happen. You should have moments where it's like, oh, I'm done. Because you don't have to go through and balance everything else. If the charges are all okay, the balancing will work out just fine.
And that brings up a good point, guys, the fact that that's when all your naming and writing equations and all that kind of stuff comes into play that we worked on at the beginning of the unit. If you start off on the wrong foot, you're going to end up with the wrong answer, which can make your life significantly harder.
Now, essentially, guys, this last one, go alphabetically under combustions, or some people call it a CHO rule because combustion deals with carbon, hydrogen, oxygen. Really, to make your life easy, pick one and run with it. We're not going to ask you to actually tell us which one you used, just use it. So combustions of things like methane and oxygen burn to form carbon dioxide and water vapor. When we look at this, the first thing I'm going to balance is carbons. When I look over here, I have 1 carbon, so I'm going to look over here. How many carbons? 1. I'm good. I'm done. All right. This is always assuming that this guy here is a 1 to start. We assume it, but we might have to come back and change it later. Now, carbon is done. I'm going to go to hydrogen. If I look at this hydrogen, I've got 4. Over here, I have 2. The reason I'm not building a table is this should work out a little easier. I don't need to go through that amount of work. To make my 2 into 4, I need to use a coefficient. 2. Okay, so now I have 4 hydrogens. Hydrogen is off the table. He is done and good to go, and the eraser does not work very well. Now, the oxygen is the trick, guys. There is 1 oxygen on the left, but oxygen shows up twice on the right. So what I would suggest is take your coefficient and take your subscript, and underneath you can just write a 2. There are 2 oxygens in water. When I go to carbon dioxide, same thing. The coefficient is 1, the subscript is 2, so 1 times 2 is 2 oxygens in water. If I was to look at this in terms of oxygens, I now have 2 plus 2. I'm just going to go backwards and say that I have 4 oxygens. Now, 4 oxygens is what I need, but they come in pairs. So 4 divided by 2 is 2. At this point, the equation is balanced. If you ever try to balance a combustion and you find that you have an odd number right here, how could we fix that odd number? Well, the easiest way is to go back through and double all of your coefficients. If we double everything, well, 2 times any odd number is really sloppy apparently, but it becomes an even number and you'll have an easier time finishing your balancing. rather than just saying it, let's try it, and then this video will be, whoops.
Oh, ruin the surprise, McLeod. Okay, let's take a look. So let's take a look at a little more complex example of combustion. Okay, so again, I'm going to make the table on this one just to kind of review what we've talked about. Okay, so we'll go CHO, CHO. Okay, because this gets a little more complicated, so let's go 2, 6, 2. Okay, 1, 2, and 3. Because remember, we've got to count both of these oxygens. Okay, it's a good way to keep it in mind. Okay, so we're going to start with carbon, just like Mr. McLeod said in the last one. Okay, we're going to throw a 2 in front of here. Okay, which makes this 2. And now we have a total of 4 plus 1 oxygen gives us 5. Okay, now we move down to hydrogens. We throw a 3 in front of here. Okay, 3 times 2 gives us a total of 6. Okay, but now that also puts another 3 oxygens on there. So now we have 3 plus 4 gives us 7. Okay, this is the odd example that Mr. McLeod talked about before, because now we have 7 oxygens. We need 7 over here, which is a problem. Okay, because we have they come in pairs like he talked about. So what we need to do is we need to double the entire reaction. So we put a 2 in front of there. Okay, this turns from a 2. 2 times 2 would be 4. Okay, 3 times 2 would be 6. Okay, and now we end up seeing all of these double down here. So now we have 4. Okay, we have 12. Okay, now we have 4 times 2 is 8 plus 6 is 14. Perfect. Okay, now we need 14. We're moving on. Okay, and 14 divided by 2 is wonderful, 7. Okay, so now we are all balanced and ready to go.
If you balance a lot of these guys, you'll actually start to notice that when you double it, that number that was giving you trouble actually becomes your coefficient. Not something you actually have to know, but if you practice enough that you notice that, it does allow you to go a little bit faster and know that you're doing it right.
So again, eventually guys, what we want to try to do is we want to get rid of doing this table stuff and just start proceeding like Mr. McLeod talked about before. But starting with the table is perfectly okay to get started and start seeing patterns. Who to bomb? You to bomb. Good work.
That was lame, Regnier. Very lame.